Okay, so it's already phone one is joined in. Can you just wait for few minutes, then we can start. Hello.
Yes,
So I have shared the PDF of that book. Okay.
Vivian Balakrishna's book.
Uh, the statistical mechanics for chemistry and material science. Some name actually. For chemistry and material science. This book was mentioned.
Do you have handwritten notes of the chapters like chemical kinetics, molecular spectroscopy?
Hmm. I have, but I don't know whether I have soft copy or not. But I have the hard copy. Hard copies I have. So
You came from home.
no, I mean chemical kinetics.
Yes, and molecular spectroscopy, these things. Physical chemistry only. The important chapters. Scoring.
Chemical kinetics. Yes, I have. No, but it is just the exam dose. It is not the total note. It is just the exam dose. Check.
I need all the chapters of chemistry, but at least the physical chemistry part, at least.
I understand. I had everything. I made you. Spectroscopy I have. Spectroscopy, organics and physical, both spectroscopy I have.
Please send this. In kinetics, I was finding some topics that are not available in some books, transition state theory and these things.
Transition theory is not available in books.
Not clearly mentioned how the derivation comes.
Okay. No, but in transition state theory, there is no derivation basically. There is some activation energy and barrier. That's it. That exponential term that appears due to the energy distribution, that you have a kinetic energy and kT is your thermal energy. So EA is the activation energy. So EA by KT obviously will guide whether the variant will be crossed or not. That's why that there is exponential term. And
It's, it's from the Arrhenius equation, but I was need the derivation for Eyring equation.
okay, okay. Hmm. Yeah, there was a derivation actually. Okay, I have chemical kinetics notes. Then I have to make the PDF because I don't have the soft copy. I have hard copy. Soft copy, spectroscopy, soft copy I have shared. Organic spectroscopy and physical spectroscopy. I think physical spectroscopy is it covered everything. Let me check on it. It's rotational, vibrational, rotational and vibrational. Yes, rotational and vibrational I have that I have shared and Raman also. Okay. In organic spectroscopy, I have shared IR, UV. It's combined PDF.
NMR,
Let me check. IR mass is also there. Mass is there. Huh. NMR is also there. 13C NMR is also there. Everything is there. Yes, everything is there. Everything is there. And quantum I already shared. Statistical
yes,
mechanics is also shared. Only the kinetic is left, right? Kinetic I have to find. I have to check actually.
everything that are available to you, please send.
Hmm.
I am preparing for JAM this year.
Yes. So you are now in third year, right?
Yes,
Okay. So you have to give the jam in February or March, when it is.
15th February.
15 February. Good.
What was your revision strategy for NET?
My division strategy. No, actually, I gave net 3 times, 4 times I gave. So last time when I cracked it, basically in that time it was a COVID. Okay, so COVID time. So basically my university was totally in online mode. There was no as such class, so I had lot of time, and that's why I can prepare like that way. Otherwise, preparing both means studying for both is very difficult. But for revision, I would say I uh, mm, used to do practice with this exam dose, and I gave the mock test. 6, 7 mock test I gave. So if you can buy a package of that mock test available from various coaching sites online. I'm saying not
Line
offline.
institute.
In institute, we took that course from the chemistry, so that's why that was included in that package. That all this mock test. So
And
I gave
online package.
online mock test we gave, and that was very helpful basically because after completing your syllabus, you need to revise those. And let's say you prepare that tomorrow I'll give a mock test, and I have one day I have to revise all exam notes and all the parts where you stuck basically, that you have to just revise, and then you will give the exam. In that way I prepared. And also I left some topics, very few, but that because for NET, I said you know one day, but because for NET and for this JAM and GATE, preparation is quite different. Because for NET, you have to leave some topics, but that is not true for JAM and GATE. You have to cover all topics as much you can cover. That will be beneficial for you always. But I gave JAM once only. So I can say that the level of JAM question paper is more or less same to any university exam, entrance exam. Okay, it's not very hard. Okay, so you have to attempt. In case of difficult question paper, there is some benefit that it because when you get the question paper now, after half an hour you can understand whether this question paper is difficult or in which side it is. It's difficult side or easy side. If it is easy side, then you have to change the approach. If it is easy side, then you have to score as much as possible because cutoff will go high. Definitely will go high. And
Yes.
I'll give you example. Uh, if it is hard, then you have to be very selective. Then you have to answer. Then you have to focus on perfection. There is two types of attending question paper because uh, first time I gave GATE in 2021. Yes, 2021 I gave. In 21 of one. Yes, in 21 I scored in GATE 50 out of 100, 50, 49 point something. And my rank was in that GATE exam, my rank was 171, something like. Okay, and
50 out of 39, 171.
171, 171 was my rank because the highest marks was 65, something like that, 63 or 65, if I can remember. Now next year in 2022, when I also again gave exam, GATE exam, that time I just appeared casually because I remember our GATE exam was on 1st March, and one day before it was CSI net result was announced. So uh, I got GRF. That's why I was very relaxed. So I gave the GATE. And I attempt total 99. I attempt out of 100, and question paper was very easy. Okay. Yeah, so and when the answer key came, I checked. I My score was 71. Okay. Uh, because I did lot of mistakes, so that's why it's 71. Otherwise, it should be better. So I thought that okay, everyone thought that because for in 49 it was 171, so in 71 it must be within 30, within 20, something like that. But cutoff goes higher
Yes.
because question paper was easy, and my that time rank was 121. So you see, in 49 it was 171 rank, and when I scored 70, 71, then it goes rank was 121. So uh, it totally depends on question paper. It's not how much you are scoring. If it is a difficult question paper, then you have to be very, very careful. You can't do negative marking. If it is a easy question paper, then you have to focus as much as you can answer. Okay. But in
Okay.
general, in case of jam, it is not very difficult, it's not very easy. And one more thing, it's general thing. It may be NET, GATE or jam, anything it is, you have to be rely on physical chemistry. Because from physical
That is my
chemistry,
favorite part.
the reason is negative marking will be very less from physical chemistry part. If you mark a question, if you giving an answer, then it's very obvious that it is correct because you are solving now, you are solving a question and it's matching with the option, or you are giving a fill in the blank, whatever it is, it's going to be correct. But in organic case, especially I'm saying inorganic is okay, but in organic case you are doing a chain of reactions after getting doing the all steps, you are getting a product, let's say, and you mark it. It happens to me, and you when the question paper the answer key given, it show that the product is same, but just the it's maybe an consumer, or you have just marked the below the plane and the product is correct answer is out of the plane. So these things happens. It's always 50-50. So if you I'm saying you should prepare organic chemistry and inorganic very well, but you have to be very uh, sincere about selecting a particular option, because in organic chemistry you will see that the options are very close to each other. It's obvious
Yes.
that it's just structural difference, maybe there something like that, otherwise it's very close to each other. But you have to, and in inorganic chemistry I would say you have to prepare very well the coordination part, very very well coordination part. It covers a huge portion. I think jam organometallic chemistry is not there, right?
It's there.
Is there?
Yes, organometallic, bioinorganic, all are there.
Organometallic, those reactions, do you have studied that reactions are there, namely Suzuki, coupling reactions. Or many coupling reactions are there na, in organometallic. I think
It
those
is
you,
it is in my sixth semester syllabus, BSc sixth semester.
but in jam it is right. If it is a six semester syllabus, that means probably in jam it is included. Okay, you have
Yes,
studied organometallic means that organometallic compounds you have studied.
reactions are also there. The Suzuki, this I mentioned on the
Reactions are
syllabus.
also there. Then you have to prepare organometallic as well, because organometallic and you can say organometallic and coordination, this covers almost 60 to 70%.
Yes, coordination has huge weightage.
That diagram all are there. I forgot now. Orgel, Tanabishugano,
Yes,
these things are very important actually. Whatever it is, you have you have to prepare. But I think in jam, let's say you have to score between 50 and 50 to 60. If you score between 50 to 60, within 50 and 60, then it is very good. You will get an IIT, good IIT, I
Kanpur
think.
also.
Huh?
Kanpur.
Kanpur, if you top first, I think first 20 to 30 people choose Bombay. Then after that, they choose Delhi or Chennai, then Kanpur, something like that, third or fourth. So you can say within 100, if you rank, then obviously you can. Okay.
Okay.
But it's okay. Jam is not very difficult. I'm saying because I did not take any preparation before jam, because we just went to visit. Even I can say I don't know whether I should say or not, but I have never seen jam question paper. Just last night, tomorrow morning was jam, and last night I just saw previous year question. And then I came to know the pattern, question pattern. But it was not very difficult. I find it was easy. Jam was easy. One majorly problem was that sixth semester you are saying, because it is just starting of the sixth semester, no? So it may be some portion you have not studied.
Yes.
That problem I faced because in sixth semester when I was studying, then I find okay this question was in jam, but that topic was not actually taught in that time.
Statistical
This
thermodynamics is there, but I have prepared this.
but these statistical thermodynamics and this advanced quantum, these questions are not asked very much. One or two questions hardly you will find because these are difficult part, right? And this is also quite advanced. This course and also the previous course that was MSc level course you have done. Okay, it's there. I'm saying it's there, but it's not that much. Maybe two questions are there, but these question basically for those who have studied. Otherwise, they
For
can't answer.
for NET, this topic is well prepared. I have for NET exam.
Yes, for NET because in NET there is option now. You can leave question. So in NET they can ask.
In physical, I don't want to leave.
There is no option, right? You have to answer all question.
Yes, yes.
So it's okay. Anyway, you have to do. Okay. Okay, so you have time, but just prepare. And there are two types of preparation. One is your preparing for exam, and one is preparing in exam. So that is also very important because when you are giving this kind of exam, na, so you have to. That's why I am saying to give this mock test. Otherwise, in those exam, it is very difficult. You have to manage the time. For that also, you have to prepare. Okay.
Please
Okay.
send the
So
name in WhatsApp.
okay. Okay. So any doubt from previous class, previous discussion video? Otherwise, and if you have any doubt from the things taught in this week, then also you can ask. Otherwise, we can start. It's already 4:20.
In this week, I could not understand the course videos.
Okay. What was the topic?
I could not hear. The voice is broken.
Oh, okay. 1 minute. Just let me connect the your headphone. In this week, what was discussed?
Some solvent effect, solvent interaction.
These things are boring. These things are not basically statistical thermodynamics or statistical mechanics. Okay,
Theory of liquids, these things also there.
these these things are basically used in the research. They did. Biman Bagji family did actually. Okay, so that's why he's teaching this kind of stuff. But this is not
Their group focus on which topics?
this statistical mechanics of this water body. Okay, but this is also statistical mechanics. So this is quite different statistical mechanics.
I am very afraid of the expressions in taught in the class.
Okay, that's it. That is important. If you do research in this field, then it will be important. Otherwise, no. Okay. Okay. So today we'll discuss first this part. This part I did not discuss in last class. I thought to be discuss this. We have studied the Lagrangian multiplier method. So from Lagrangian multiplier method, we can calculate first the most populate state that we can calculate that we have not calculated in last class for all types of distribution, Maxwell Boltzmann, Bose-Einstein, and Fermi-Dirac, all three that we can do first thing. And if you want to do, then I can derive that that expression in last class we discussed now that uh, the number of microstate, that formulas. Do you want to discuss that things, or otherwise we can jump into those part?
Is it possible briefly?
It is not difficult, but you have to think. It's not rigorous derivation. Okay, that's why I'm saying. Okay, just I will share the note today. Okay, and then you just go through it. If you find you just read it. It's hardly 2 or 3 page. Hardly 1 page.
Then I will do it.
Huh. It's just it's not derivation. It is just written there. You have to just read it and think it, and then you can understand it. It's like that. So this part they
Okay.
so today let us discuss this part, and we will do some problems also. I have think of. Okay. Okay. Let me share the screen first. Okay. Is it visible?
Yes.
Okay. Today we'll discuss. Okay. So this form we have done for a particular orientation or occupation type, whatever you want to say. We know that gamma omega, sorry. So it is written as
-1. Yes.
this formula you have to remember. These three formula So now our task is we have to find out the Ni star. That means this Ni, what is Ni? Ni is the number of population in ith state, right?
Eighth state.
Quick, right? And Gi is the number of degeneracy of that ith state.
Yes.
So we have to find out that which state among these k state, there are i's running from 1 to k. So among these I equals to 1 to k, which state is mostly populated? That we have to find out. Okay. So how you can do that? What should we do?
Calculating its maxima
So how we can calculate the maximum
by taking the derivative.
of which? We have to take derivative of this ln rho, ln omega,
Yes, ln
or
omega.
omega, whatever it is. But we know that the dealing with
It's
ln
easier.
omega is easier. That's why. So first, let us start with this one. So let us start with Maxwell Boltzmann. So what will be ln Maxwell Boltzmann? Ln of n factorial
Plus
plus,
ni ln vi.
okay,
Yes.
particle. So this is a constant term, right?
Yes.
So and this can be written as summation. So how we can simplify these things?
The ln ni factorial we can use Stirling approximation.
Exactly. So it is clear. It is just ln gi. Here we have to use a Stirling approximation. Minus.
Minus ni.
Okay. So it is again a constant because it is actually total n.
Total n. Yes.
So you can absorb it in the constant. Perfect.
This is called constraint.
Constant. It's a constant number. Na? N is a constant. N is
In
total.
Lagrange multiplier, there was some constraint. Total number would be
That
constant.
is different thing. That when we will do derivative, then we will apply. Now we are not doing derivative. We are just simplifying the expression of this ln omega.
Okay.
and then you can write it, right?
Yes.
So now we'll take the derivative. So what will be this? Obviously, you are taking derivative with respect to n, right? That is perfect. So constant, this part will not contribute.
Yes.
And from this part, we can break it like,
First term ni derivative will be 1 and ln gi will be there.
okay.
Yes. In the first term, I am not getting the ni there. The next line, 0 plus this term.
Hmm. If you take the derivative of these things, it's just u times v na. So u dv plus v du.
Okay, I'm just mismatched it.
Just check it.
I'm written the second term first and the first term second. Okay.
Oh, that you can write. What will be this? Gi is the degeneracy, right?
Yes.
So ln of degeneracy, this is just a number.
Yes.
So it is zero. Because ultimately you can these things can be done like this way as well. Gi certainly is not depending on ni, right?
Yes.
So this part you can it is zero. So ni. You see, we are not using Lagrangian multiplier till now
Yes.
because there is no restriction. Okay, so it is ni and delta ni. This you know it will be 1 by ni times delta ni,
Yes.
and this part is clear. This is just same thing, nothing to do here. So if you simplify it, perfect.
Yes.
This is delta of ln mb. Now you know for maxima this delta for finding out the extrema, that may be maxima or minima. You know this should be 0, correct?
Yes.
But if there is no constraint, if there is constraint, then you have to use Lagrangian undetermined
Multiply.
method. Okay, and you know
Yes.
that this const, what is a constant? This is a constant, right?
And energy.
And energy. Okay, and these are the constant alpha and beta. So it will be perfect. Now we will put it here. What is alpha time delta ni? How you can write it? Can you write? Is it okay?
Writing this line.
Write it from here to here. Is it okay or not?
I am checking once.
Okay, okay. Just check, then I will go ahead.
The beta term is not matching.
Beta I have not written till now.
Okay, I am also getting this.
Okay. Because you know summation and derivative always comment.
Yes.
Okay. Then just this is okay. Because a delta ni is the only thing. There is not changing epsilon I.
Yes.
So as a whole you can take disturbing actually. I have ordered a it
Okay.
and you can take the beta inside as well. There is no problem. Okay.
Yes,
Yeah. So from here, what you can write?
this
Which thing
tab is
should be
equal to
zero?
0. Tail ni should not be 0
Why?
because the number of particles are not constant, they are changing.
It may be constant.
If I heat the system or work done on the system, then
I am not
it will.
doing any work done, anything, nothing. I'm just maximizing the omega. That's it. So number of particle is the variable actually, obviously. Then what's the logic?
In a
Delta ni,
system, the total number of particles are not constants.
that is constant.
If
It's a
the
closed
system is
system.
interacting with,
This is not grand canonical. See your constant, Lagrangian constant, that is for canonical, right?
yes,
Then delta ni, it may be zero or may not be. So it can take any value, right? So it's
yes,
arbitrary, arbitrary. So delta ni is arbitrary. So that means, but it is always zero, correct? That
yes,
essentially means this should be always zero. Got it?
yes,
So and when it is zero, you know that is the most populated state.
yes, LNI star.
So it can be written as ln. Okay, one dummy variable.
Yes,
Perfect.
yes,
That is the state, eigenstate, which is mostly populated. So that you see, that depends on alpha, beta. These are constant, okay, but it depends.
yes.
Yes. Okay. Now, in the same, so this is the extreme most populated state. Actually, Ni is the populated. Gi is the, yes. So you have to now calculate actually. Alpha, beta, you know. Gi, you know.
Yes,
Is there any example? I'm just checking. This is special. case. That's okay. 1 minute.
At very low temperature, only the ground state will be populated, and at high temperature, all will be equally populated.
That's okay. Yes. Mm, mm, okay. When the so what is this Ni star? What is the physical significance of Ni star that I am uh, looking for? Can you explain?
The state where the molecules are maximum among all the states.
Then why there is suffix I?
Then,
There is a suffix I, right? So let's say that means you can calculate Ni1, N1 star, N2 star, N3 star. Then what is the meaning of star? Can you understand what I am saying? It is
in
not,
which condition the N1 will be maximum?
it, it is the number, it is actually the uh, what is the highest value of that highest population can be of the state. Okay, let's say if it is N1 star, that means it is the N1 star is the maximum of N1. Do you get it?
Okay.
Means which population can be the boundary, upper limit of that population.
N1 star is the maximum value for N1.
N1. That's why there is the star now. That is the case. Means for that value, N1 star, for that value, the omega will be maximum. Microstate will be maximum. That is the case. You are finding the population of a state, particular state, for which the microstate will be maximum. That's the case. Yes. It is not among all I state which one is mostly populated. No. Then there would not be any star. I. You are not doing that.
The microstate under the IS state.
No, no, no. Microstate, let's say there are four states. Populations are N1, N2, N3, N4, correct?
Yes.
So now, depending upon this population, this omega will change
Yes.
because what is this omega? You know, N1, N2, N3, N4. From there
Total
you
n
can
factorial
calculate the
by.
omega, right?
Yes.
And you are finding that highest omega, maximum number of microstate. That's why you are ln making ln omega 0.
Yes.
So for making ln omega 0, you need N1 star, N2 star, N3 star, N4 star. Each are these.
All are stars.
All are stars. Then only, na? Then only this omega will be maximum. Otherwise, how you can say? That's why there is I, you see?
All the state are populated maximum.
No, all the states are not at populated maximum. That I am saying. These population can be different. Let's say there are how I can say total number of particle is fixed, na?
n1 plus
Yes.
n2 plus n3 plus n4. Let's say that is 10. So this may be, what should it be? If it is 12, you know, this is 3, 3, 3, 3,
Yes.
like that. Then this will be maximum, like that. You
Yes.
are
Then it will be
finding,
highest.
this.
Okay.
Okay.
But it should not be always 3333. That you have to calculate it.
Equal will be always greater than anything. Yes. Canonical answer.
E is already there. So n1 star and n2 star all will be not equal. Surely.
Yes.
It may be any other thing. You don't know. So you have to take all the orientation. Let's say 1, 10, 0, 0, 0, 1. This is the one orientation. You have all that. And then you have to calculate the omega, considering this formula n factorial, this di to the power ni divided by pi of ni factorial, right?
Yes.
Then you will see which one is maximum. That this is that formula. By using this formula, you can directly find out n1 star, n2 star, n3 star, and n4 star, for which this ln omega will be maximum. Do you get it? And this is not
Yes.
necessarily all states should be equal. In canonical ensemble, it was, but here it is not. Okay,
Okay.
because in canonical ensemble, you are finding the in between distribution, not the energy levels.
Yes.
They're different things. This is the molecular energy level. This is quite kind of different thing, because in that case this formula was, what was the formula? That n factorial divided by
By n1 factorial and 2 factorial and
ni is there.
yes, the degeneracy.
That is the problem. Okay. So we'll do some example, then it will be more clear. Next, can you do it for both Einstein?
This same thing.
Same thing you have to do. You have 5 minutes
Yes, I
only.
can do. Yes.
In 5 minutes.
5 minutes.
Hmm. It should not take more than that. It's one page. Just follow the same description.
Should I do now?
Hmm.
Okay, I'm doing.
If you can't, then I will. Anyway, I will do, but I want to see whether I can do it or not.
Okay, I'm trying. Both Einstein.
Both Einstein one is easier.
Sum of the degeneracy is constant or variable.
Degeneracy, not constant, but some of the degeneracy is number, and that is not depend, just like here, right?
Yes.
What are you getting?
I am doing the last step. I am stuck at the last step.
With the line.
The derivative of the ln ni plus gi minus 1.
You just say this ni star.
In the numerator, it's gi minus 1 into ln gi minus 1 something.
Repeat it.
But
Repeat it.
gi minus 1 into ln gi minus 1.
In the numerator
Yes.
and denominator.
Okay, let's do this. You just follow. Okay.
Okay.
Oh, where it is not matching. So, similarly, we'll first derive what is ln of omega beta e. So directly it will be summed, right? Is it okay?
Yes, I have also done the same.
You have also done the same. Great. But now we'll do some approximation.
Starling approximation.
No, before that. This Ni plus Gi must be very greater than one, right? That
Yes.
we can ignore one. That's all. Must be. Ni, Gi both are very greater than one. Perfect. Or is there any doubt?
I have not done this thing.
That's why you have getting that one term, right? I think so.
Yes.
Let us check what happens. So now we'll use the standing approximation. So it is ln. No. Okay.
Yes.
Now it will cancel. Right. Yes. Now you have to maximize it. For that, you have to calculate first this. So you know delta and summation always commute. So directly you can write
Yes.
first this These two term will be there, I guess. Because GI is not important here. You know,
Yes.
that is just a number. So now what you can write? Write this is just as a delta Ni. Because delta GI again will be and this will be this, correct? Is it okay? How I can do it? This is okay. So it will cancel.
Okay, I'm getting this.
So it is eventually just delta Ni minus delta Ni, these things. Hmm. This is just ln. Okay.
Yes.
And next part, we have to use Lagrangian undetermined multiplier method. So it is okay. So similarly, we have to just take common totally. So again, this is arbitrary. So this part should be 0. So again,
Yes. Alpha plus beta. Yes.
let me write just one step. And now when I make it 0 means it is start.
Yes.
So this is the answer. Can you see the difference between the Bose-Einstein and the Fermi-Dirac? Only this term, right?
Yes, the minus one.
Minus everything is same. Now, following the same procedure and keeping in mind the same logic, can you do the Fermi-Dirac? That is also will be similar. First, can you guess the answer for Fermi-Dirac?
Plus one.
Exactly. Now, can you derive it?
Yes.
Right. Now it should be done, right?
Yes. The same approximation will be used
Same
here also.
approximation if needed. If needed. Know the answer. That approximation is needed or not?
Not needed. The del LNGI part will be 0.
Yes, because GI is a constant number, right? That is not dependent on NI.
Yes. I am getting 2 minus 1 term in the expression
2 minus 1 term.
after the derivative.
2 minus 1. It is not matching.
Okay, no, they are cancelling out. Sorry. Okay, I got the last line of the answer and got the answer also.
It matches, right?
Yes.
Okay. Then just let me do it very quickly. Okay. So you can also just check the steps. FD is
GI factorial by NI factorial GI minus NI factorial.
so one thing can you predict from this expression if there is if there is no degeneracy, then what will happen?
Then the GI factorial will be 1.
But the denominator,
NI factorial into 1 minus NI factorial.
if gi 1 minus ni factorial, correct. So what does that mean? What is the significance of that expression? You see, that essentially means for a right state, particular right state, I'm saying it's clear that gi should be greater equals to ni.
Energy should be greater than the particle.
Hmm?
Degeneracy is greater than the particle number.
Either greater or equal.
No two particle can be in same state.
Exactly. Why this is? Because it's a Fermi-Dirac particle. Because the occupancy is either 0 or
1.
1. So this should be no other option. If GI is, let's say, that I will do later. If GI is 1, then what will happen? That we will see later. But I'm just taking the hint. Okay. So what will be ln FD?
Yes, these are cancelling.
Hmm. Now you know that delta. What will be that? First part will be anyway 0. Only
Yes.
second part will contribute. Minus. So minus minus will be plus. Is it matching? The steps are matching?
Yes, I am also doing the same.
Okay.
I have done already.
Yes, that you have done. But here what will be 1, right?
Yes, that what I am saying.
Alien Ina is there. Am I miss something? Did I miss
One,
something?
one LNNI term is there.
That must be. Oh, it was here. NILN. I missed it.
NILNNI.
Sorry. These two terms.
And the NILNI term will be -1.
Delta NI.
Yes, this one.
And delta NI will be cancelled out. So it will be
Yes,
just, it will be just minus this.
yes,
So now Lagrangian multiplied if you apply. But you can write now. Okay. And again, this logic is known. This should be arbitrary. That's why
yes,
this part should be 0. Again, I missed. There is one more term, minus 11.
yes, -11.
Okay, so it is 0. That essentially means Ni is Ni star. And now we can write ln. So it can be written as
Ni star equal to gi by e to the power alpha plus beta I plus 1.
this is okay. And so in general, what you can write? General formula that will be,
Gi by e to the power alpha plus beta ai plus minus or 0 plus minus 1 or 0.
so it is called eta. So eta is 0 for Maxwell-Boltzmann, is 1
Minus 1
for Bose-Einstein, minus 1 for Bose-Einstein, and plus 1 for
Fermi Dirac.
okay. Now you will see some special cases. First, if Gi is 0, Gi is 0, I am saying Gi is 0 means for all state are non-degenerate. It is not a particular state is non-degenerate. It is for any I. Okay.
Okay.
So then what will be the gamma in first Maxwell-Boltzmann? It was n factorial
Gi to the power ni.
ni, and it is
Ni factorial.
gi.
Product of ni.
So if Gi is 0 for all I, so it is directly you can write it. And this formula was known to you.
Yes.
But what will be for Bose-Einstein and Fermi-Dirac? Divided by?
Ni plus
What
gi
was the
minus.
formula? I forgot.
Ni
Gi
factorial
minus
into
1.
gi minus 1 factorial.
So it will be
Ni minus 1 factorial by n factorial into minus 1 factorial.
what is Gi? Oh, sorry, Gi can't be 0.
1.
1. 0 means not 0 means no state is there. Sorry. Gi
Yes.
should be 1. That means not there. All state are non-zero. It will be
Ni factorial by ni factorial
so it is
1.
1. That means only one microstate is possible. If all
All are
states are
in the same state.
non-degenerate, then only one microstate is possible. Why? That means I'm saying, let's say there are 4 energy state. You have 10 particles, 10 bosons because it is Bose-Einstein. Now, if all states are non-degenerate, then only one arrangement is so means one under that occupation obviously means occupation means let's say 3 3 2 2. This is occupation, correct?
Yes.
Under that occupation only one arrangement is possible. Why? One microstate is there under this occupation or orientation, whatever you want to say.
Because the particles are indistinguishable.
Exactly. Because the particles are indistinguishable. You have no other option eventually, you see.
Yes,
For Maxwell-Boltzmann, particles are distinguishable. That's why that is not one. But you see, if you make just one level degenerate, any level degenerate, then obviously options arises. Correct? So if those
yes,
states are non-degenerate, then for a particular orientation or occupation, you will have only one microstate because particles are indistinguishable. And what will be for Fermi-Dirac? Can you guess it? For Bose-Einstein, you see, what will be for Fermi-Dirac?
I am calculating it.
Okay, calculate.
1 by ni factorial into 1 minus ni factorial.
So what will be the answer? Bosons
1
are
minus
indistinguishable
1 by 1
fermions.
minus ni factorial.
Okay. No, I'm saying bosons are indistinguishable. Fermions are.
They are also indistinguishable.
So the answer should not be changed.
Yes, it should be 1.
It should be okay. Or
But
0.
I am unable to calculate it.
Because here you have to invoke some physical thing. It is 1 factorial. Perfect. It is ni
Yes,
factorial. It is 1 minus ni factorial. Correct?
yes,
Now ni can be
yes, 0, 1.
because you know gi is greater equals to ni and gi is 1. That's why. So if ni is
Yes,
0, then it's directly it is 0. Nothing is there.
yes.
It is 0. No, no, no. Sorry. It will be 1 factorial by 0
1.
factorial by 1 factorial. So it is 1. And if ni is 1,
Then also it is 1.
then it is 1 factorial divided by 1 factorial divided. But this does not make any sense. There is no particle in
Yes,
any state. So that does not make any sense. Okay. So this is the case. So it is 1 always. Okay. Now the last part we'll discuss, that is the if gi is very greater than ni. This you know because we have already calculated the available state in last class. That was very
yes,
greater than ni, right? So
yes.
this is a physical approximation. So what will happen? Let us see. And you know this is called, what was called classical limit, correct?
Yes, classical limit.
Occurs in high temperature and low density, right?
Yes. What is the relation with low density? Means
That there
volume
was
is
something
very
E
high.
by A cube terms was there, na? That is the density
Yes.
due to that. So first let us start with the Fermi-Dirac.
Ni factorial into gi minus ni factorial. The gi minus ni factorial will only gi factorial. Answer is 1 by ni factorial. gi minus ni factorial is gi factorial when gi very very greater than ni.
Can you do that? Can you do that? Let us do generally first. So you can write it. Gi factorial can be written as gi, gi minus 1, gi minus 2, and so on, right?
Yes,
So you will definitely have a term like this.
yes. So here I can start by gi minus ni into gi minus ni minus 1.
Hmm. So no, it is wrong.
If I
So
break the gi minus ni factorial,
next term should be gi minus ni, right? Then it is gi
yes,
minus ni plus 1 because it is decreasing like that.
the whole term till 1 will be gi minus ni factorial on the numerator.
Numerator?
From gi minus ni into gi minus ni plus 1 to till 1.
Yes,
The
yes. So you can write it as like, and it is gi minus ni factorial, right?
yes,
So this will cancels. Till now, I am not applying any approximation or any assumption.
yes,
So it can be written as this one. So is I can write it gi to the power ni divided by ni factorial or not? Because this means all terms gi, and but these are the less than gi, right? All terms, so it is valid.
okay,
Okay,
yes,
means obviously including this. Perfect.
yes,
Now, so here I am not applying this condition. It will I will apply later. It is general law,
okay.
general case for Bose-Einstein. You see, we are just uh, creating relation with respect to Maxwell-Boltzmann. This is Maxwell-Boltzmann, right?
Yes,
We just want to compare Hermitier, Bose-Einstein, and Maxwell-Boltzmann. So Bose-Einstein was
ni plus gi minus 1 factorial by ni factorial into gi minus 1 factorial.
okay. So now let's say hi equals to gi minus 1. You can assume.
Yes, why we take hi factorial?
And otherwise, we have to just carry gi minus 1 this term.
If we neglect the one term,
Okay, let it be here now. Make it general. Later we will do if needed.
okay,
So it can be written as
hi factorial.
because uh, you will have some this term you will obviously get, right?
Yes.
Same thing we are just repeating. You see, if you this, then you have to repeat it, ji plus 1, it will look odd,
Yes.
and so on. Okay, so what if this? So you can write, can modify this, just modify this, you will have. So first term, this is perfect. What is this term? Hi, is it okay?
Yes.
So definitely it is up to
Ni plus hi minus. Yes.
hi
Hi
plus 1,
plus 1.
right?
Yes.
And it is h factorial and ni factorial by h factorial. Okay,
Yes.
so definitely what you can write it,
Till gi.
so it is always be greater equal to, not greater equal, greater. Why? Because
Ni is.
all terms are greater than gi.
Yes.
This you can write. So surely Fermi Dirac is less than Maxwell Boltzmann divided by n factorial, because you know here n factorial term was there,
Yes.
and you can write Bose Einstein is always be greater equals to Maxwell Boltzmann by n factorial. Correct?
Yes.
Now, if you apply Vi is very greater than Ni, then what will happen? Just see first the Fermi Dirac. Gi is very greater than Ni, then you see if Gi is very greater than Ni, then these all terms will be more equals to Gi, right?
Yes.
So this less than sign will be very close to this part. Okay,
Yes.
means it is, let's say, 1000 and Ni is 3, then it is 1000, 999, 998, and 997. This divided by n factorial, and this part is 1000, 1000, 1000. So it will be very close, correct?
Yes.
So that is the reason. And here also, if Gi is very greater than Ni, then obviously you can write both will be very close. So FD, but Obviously, it will always be less, so slightly less, and Bose-Einstein is also more or less Maxwell-Boltzmann, but slightly high. Okay, that means what you can say at classical limit, you can use Maxwell-Boltzmann, right? Both Fermi-Dirac and
All are
Bose-Einstein
same.
distribution can be replaced
By
by
MB.
Maxwell-Boltzmann. Okay, that's why it is called the classical limit. Do you get it?
Yes, the classical limit means the degeneracy is much greater than the particle.
Yes, and I just gave you the example 1000, but GI is 10 to the power 7 times greater than NI.
Yes.
So obviously it is valid. Okay.
Yes.
So now you can try this. We have done today everything considering only Ni is varying. Epsilon I is not varying. So you can try if epsilon I is varied, then what will be the expressions?
For
Okay.
grand canonical.
No, no. The population can be changed or energy level can be changed, na? Both can be
Yes.
changed. But here, if you remember, we have when this beta, this we have not included. We have only delta Ni is there. Epsilon I is not there.
If I do this, then what will I consider for the Ni? Will it be constant or variable?
Obviously, Ni will not be changed in that case.
Only Ei is the variable.
Ei is the variable.
Okay.
You can try. It's not easy because there is no direct term of Ei. Gi
Yes.
will be dependent on Ei, but that is not explicit. I'm just saying there is a point. Okay. So in next class will be our last class, right? Uh, so in next class we can do. I don't know whether I can read it or not. If I get time, I will read this part. But mm, otherwise, we will do that statistical part. I'm thinking statistics part. Okay,
Okay.
that cumulants, moments, these things in detail, distribution, these things we can discuss. Okay. That extra class mail came, but I did not notice actually. In this week, I did not notice anything. So mail came and date was actually gone. I have to mail them whether they will approve or not. I'm not sure. If they approve, then I will take the extra class.
Okay.
Yeah. And the exam dose I had means I have gathered from other. I send you. Okay,
Okay.
just check it and that note I will arrange. Okay, so let me now stop sharing. Only chemical
Okay.
kinetics, right? Spectroscopy I gave.
Yes. And any other physical chemistry important topic? I don't remember now.
I had everything, even I have, but I have to make PDF. You have to just ask me what topic you need. Then I will do. I have to make the PDF, right? That's it.
What topic is important
Mainly
after?
quantum, statistical mechanics, thermodynamics, spectroscopy. These things I gave to you, so these are enough. Kinetics I will give. That's it. No other topic is in physical chemistry. Group theory is there, but group theory is not very much important for there.
Yes, it is not in BSc.
Mm. So that's it. No other topics are there.
And the application of thermodynamics part.
In thermodynamics, it has everything. I shared you note, na thermodynamics note.
Yes, but the colligative property part that are not mentioned
That
there.
I did not study. That part is way boring. You One thing you can do for colligative property part, just important formula you just look. If you like to read it, then read it. It was not my type of topic. That's why I left it. Okay. Otherwise, you can just go through the question, exam those or just the uh, questions. And you have studied in class 12, right?
Yes,
That is enough. And that is enough for jam.
yes, I have seen the questions are
Hmm.
no much easy.
Just read from class 12 book for this colligative property part. Don't go in azeotropic. That is very um, boring, irritating, and probably 1 2% will be there, but it's okay. But study this phase diagram. This part is interesting, right? This I also
Yes, this
discussed.
part I have done.
Uh, that is okay. If you done that part and this colligative property from class 12, it is enough. It is enough. After
Okay.
that, if you have to leave 1 2 question, it's okay. It's
And for the statistical mechanics part, which things I can read after this course and this all?
I will upload this to entire PDF today.
No, no, I am saying after this course to
After this course, everything about statistical thermodynamics and mechanics you know from molecular part, from this course and the statistics I will discuss in next class. So you have covered everything statistical mechanics. So nothing left.
in the field of thermodynamics, if I want to know something
That
new.
is for research. That is advanced. That you don't need to like that density matrix approach is there. Many other approaches are there. That is not important. Right? That is
Okay,
quite advanced. This is up to MSc level. You have covered everything. I can say
the statistical part
yes. Statistics part I will discuss in next class. Then it will be
in thermodynamics in the MSc syllabus, is there
you have
anything
covered
new?
everything.
Chemical thermodynamics.
Chemical thermodynamics, I am saying. Chemical thermodynamics means classical thermodynamics, right? That gives Dewey equation, that part, those part, that and numerical. That
Yes,
is easy. That was also discussed in previous. No, that okay. That course probably you was not there. Were not there.
I have seen it from the YouTube
Okay.
channel.
There I discussed this classical thermodynamics also. Thermodynamics is statistical thermodynamics and thermodynamics both are almost covered.
In the syllabus of IIT Kanpur, I was seeing that in the MSc there was non-equilibrium thermodynamics syllabus.
Yes, non-equilibrium thermodynamics is something else. That is in
In
MSc.
yes,
No, but there are some elective courses are there. They are that are advanced course basically for PhD student, but MSc student can also do like that. Those courses are very advanced. Non-equilibrium thermodynamics, some quantum electrodynamic courses are there. Some path integral courses are also there. These things are there, but you can't consider those as a regular course. That is not. We studied non-equilibrium thermodynamics in our MSc, but if any course run in next semester for non-equilibrium thermodynamics, then I can discuss. That part is missing. Yes, these thermodynamics is statistical thermodynamics, but equilibrium, obviously, not non-equilibrium.
after my exam, can I start this topic little bit?
Yes, if you need note, I will share.
Okay.
I will share to you. But eventually, you will study in MSc. Wherever you do, this is there. Non-equilibrium will be there, but not great in detail. But it will be there. Okay.
Next
So
week the timing will be same.
same fourth.
Okay, thank you.
Okay. Okay. Again, we will meet in next class.
Thanks for joining.